In this lesson, we're going to talk about reflections and the concept of a controlled impedance trace. The concept of a controlled impedance trace is often difficult for PCB designers to grasp. First of all, what does it mean that a trace has impedance? A trace is a piece of copper. Its resistance is so low that it's negligible most of the time. So, what do you mean that a trace has an impedance? And even if it does have an impedance, how do you control it? And then the problem of trace impedance isn't the problem anyway. The controlled impedance trace is the solution to the problem. But it's not even the complete solution. So this whole thing gets kind of confusing for designers to get their arms around and grasp. And so we're going to start trying to bring some sense out of all of this in this particular series of 3 lessons. First of all, the problem is reflections. And let me give you a rule. If a signal propagates down a conductor, it reflects back toward the front of the conductor. If any signal propagates down a conductor, it reflects back toward the front of the conductor. Always. There's only one very specific exception to that rule, and that exception is so specific that it's virtually impossible for it to happen by accident. The engineer would have to specifically design in the circuit to prevent the reflection if that's going to happen. Otherwise, it is always true that there is a reflection back. Well, that raises some interesting questions. What do the reflections look like? Why haven't we been more worried about this in the past? I just established this as a general rule. It's been around forever. How come we haven't worried about it in the past? Why don't we worry about this on all traces instead of only some traces? What makes some traces different from other traces? And what determines which traces we have to worry about reflections with and which traces we don't? These are all very good questions. So the first question is, what do reflections look like? This is a little transmission line simulator that we designed at UltraCAD that I use in a lot of seminars. It is available on the UltraCAD website. I'm going to call this program up and run a couple of simulations for you to show you what reflections can look like. And here it is. We have 3 windows in this simulator. The first is a trace or a conductor. The horizontal axis is distance. So here's the beginning of the trace. Here's the end of the trace. And we're going to send a signal down the trace. This window shows what's going on at the beginning of the trace. This axis along here is time. So that's showing what is going on at this point, at the beginning of the trace. This window shows what's going on at the end of the trace. Again, this axis is time, and that is showing what's going on right down here. Now, I'm able to send 3 different types of waveforms down this trace. A step function, a single pulse, or a square wave, which we hope what our clock signals look like. I'm able to start and stop and pause the signal as it goes down the trace, and I can adjust the speed as it's propagating along the trace. We're not going to get into too much depth on this right now. This trace is already designed as a transmission line. We're not going to worry about that kind of stuff, except at the end of the line, I'm going to tell it that there's a very large resistor at the end of the line to simulate an open circuit. So what I've got is I've got a driver. It's driving a signal down the line. There's an open circuit at the end of the line. I'm going to say that there's going to be a reflection back up the line, and we're going to see what it looks like. So we're going to send a single pulse down the line, see what happens, and here comes the pulse. Here's what it is at the beginning of the line. Here we'll see what happens down here when it shows up at the end of the line. And when it gets down to the end of the line, bang, there's a reflection. And it starts back up the line toward the front end. Okay? Now what happens if I give it a very low resistance at the far end of the line. Let's just say I put a 10 ohm resistor down at the far end of the line. And I send my signal down the line, and my gosh, there's a negative reflection at the far end of the line. And that's a funny looking thing coming back up here. So if I have a high impedance, I get a positive reflection. If I have a low impedance at the end of the line, I get a negative reflection. What happens if I send a square wave down there? Let's send a square wave down through a line that's got a high impedance at the far end of the line. This represents a clock signal. I'm just going to let this thing kind of free run. And now we see what's going on down the line, and even to the untrained eye, that's pretty ugly. It's not likely that our circuit is going to work if we think we have a clock pulse going down the line and it looks something like that up and down the line. Okay, well, if we put a real low impedance down there and do the same thing, we still get something that's pretty ugly when it stabilizes, and it's not likely the circuit is going to work here either. But here's an interesting thing. Without understanding why I am going to do this yet, let's just put a moderate resistance down there at the end of the line. Let's say 65 ohms. Now the line is a 50 ohm line. That's all right. I'm going to put 65 ohms down there. As we get farther along in these lessons, we'll kind of fine-tune our understanding a little bit about what's going on there. But for now, just say I'm going to put an intermediate impedance down there. I'm going to send my square wave down the line, and when it all stabilizes, it starts looking like this. That's not perfect, but it's not too bad. And so, maybe this is going to work. That's a judgment call that somebody's going to have to make. But there's a pretty good chance that in this kind of situation, the circuit would work. So what do we get out of all this? What do reflections really look like? Well, the sign and the magnitude of the reflection depend on what's at the end of the conductor. And sometimes the reflections are small enough that they don't interfere with the signal. Well, that's confusing enough. So why haven't we been more concerned about this in the past? Well, the impact of the reflection depends, first of all, on the trace length. So I've got 3 simulations here. These simulations are done with the Hyperlinks Signal Integrity Simulator, now available through Mentor Graphics. And I've set up simulations with 3 different trace lengths called X, 2X, and 4X. I've just arbitrarily selected them, and I've arbitrarily identified them as a short trace, a long trace, and a critical length. And as we go through this lesson, we'll start to understand the impact of that and what that means. In the short trace, the black line is the driver, the red line is the signal at the end of the trace, and we see in this situation that the signals align themselves pretty well and actually look pretty good. So when we have a short trace, even though this is an open line at the far end, and there are some reflections coming back, the reflections are kind of small and not providing much of a problem to the circuit. When we have a long trace, well, then we have our driver. We've got the signal at the far end of the trace. There's a bunch of reflections that are set up. The reflections are even impacting the driver. This looks pretty ugly, and probably the circuit is not going to work under a situation like this. This length, which we call the critical length, the driver looks reasonable. There are some problems here with the reflections that are set up, but this circuit may or may not work. That's something that would be yet to be decided. But clearly this is a situation that is between a very good situation and a very bad situation, and this maybe will work. Well, now that's all pretty confusing also. And what do we mean by these kinds of trace lengths? and we're going to talk about the difference between a short and a long trace length. And the difference between a short and a long trace length depends on the relationship between the length of the trace in units of time and the rise time of the signal. It's not the length of the trace in units of distance. It's the length of the trace in units of time compared to the rise time of the signal. And a very short trace is one in which the signal gets to the end of the line much faster than its rise time. So a very long trace is one where by the time the signal gets all the way down to the end of the line, the signal at the driven end has already stabilized long before the signal gets to the end of the line. And the critical length is typically defined in our industry as when the two-way delay along the line, that's an awkward way of stating something, when the two-way delay along the line, which means the signal round-trip time down and back, equals the rise time. So when the length of time it takes for the signal to get down the trace and back again, when that equals the rise time, we call that the critical length. So now, why haven't we been more concerned about this stuff in the past? Well, when the two-way delay along the line, or the signal round-trip time, equals the rise time, we can build a table that looks something like this. If we're dealing with a rise time of 50 nanoseconds, that equates to a maximum frequency harmonic of about 16 megahertz. The critical length, according to our definition, is about 150 inches. Almost nobody was building circuit boards with traces that were 150 inches long. If the rise time was 10 nanoseconds, well, that equated to a maximum frequency harmonic of about 33 megahertz, and the critical length was about 30 inches. When the rise times got as fast as 1 nanosecond, well, that equated to maximum frequency harmonics of about 330 megahertz, and the critical lengths got as short as about 3 inches. When the rise time gets as fast as 1/10 of a nanosecond, equating to a maximum frequency harmonic in the 3 gigahertz range, well, the critical length gets almost down to about 1/4 of an inch. Now, in the past, we were working in these kind of ranges. You know, if we got a critical length of 150 inches, well, there aren't very many traces on circuit boards that are 150 inches long. In fact, the people who needed to worry about these kind of problems back then, when we were dealing with these kind of rise times, were people who were building communication lines between systems, or say between a transmitter and an antenna. Those guys had to worry about it. But those of us building circuit boards and wiring up stuff within a box weren't dealing with these kind of lengths and didn't have to worry about them. It wasn't until we started getting rise times up in this range that the critical lengths came down short enough that they began having an impact for us on circuit boards. That's when we began to worry about reflections on circuit boards. Now here is an illustration, and here's an example. Here's a driver, here's a receiver, there's a length X down to the receiver, here's a driver, here's a receiver the same distance away, then here's another receiver way down here, and a terminating resistor. Here is my driver, my driven signal that goes up like this. Let's just pick a point on the driven signal, like here. Here is the distance X between the driver and the first receiver. There's going to be a reflection back to the driver for the same distance, X. And at that point in time, the driver is still driving. So this is considered a short trace. This is a short distance in terms of our relative distances, short, long, or critical length. The signal can get down and back again before the rise time completes its transition back at the driver. But if we look at this same point on the trace and come down here to B2, and then for an equivalent length of time, come out here until the reflection comes back to the driver, well, by that time, the driven signal has long since stabilized. So if we send a signal down here and it reflects off B2, by the time it comes back, well, this signal has long since stabilized up here. So the distance from A to B2 is a long distance. The distance from A to B1 is a short distance. So here are the takeaways from lesson 2.1. The problem we're dealing with is a reflection of the signal from the end of the trace. The magnitude and sign of the reflection depends on what's there at the end of the trace. And in general, reflection is a problem if the trace is long relative to the rise time. And we have this concept called critical length that kind of arbitrarily separates a short trace from a long trace. In lesson 2.2, we're going to talk more about this solution.